The two primary operating modes of the VFSGs are start mode and generate mode. In start mode, the 235 volts AC bus applies current to the three-phase stator of the exciter generator. The 235 volts AC current induces AC into the exciter generator rotor. The induced AC current flows through the rectifier assembly, where it is converted to DC current. The DC current is sent to the rotor of the main generator, basically turning the main rotor into a 6-pole magnet. Click forward to learn more about the magnetized rotor. The magnetized rotor has 3 north poles and 3 south poles, as shown in the diagram. The main stator has electrical conductors around its circumference that alternate between the 3 phases of current. Together, these will be used to turn the rotor. Once the main rotor is magnetized, the CMSC can sense the main rotor magnetic flux vectors, d-axes, through the resolver feedback. Based on the position of the main rotor magnetic flux vectors, the CMSC then maximizes torque by supplying the necessary 3-phase current to the VFSG main stator, creating main stator magnetic flux vectors, I sub q, positioned at 90 electrical degrees, leading to the main rotor magnetic flux vectors. This torque causes the magnetic poles of the main rotor to pull toward the main stator magnetic flux vectors. As the main rotor rotates, the CMSC uses the resolver to sense the new position of the rotor. Based on the new position of the rotor, the CMSC then adjusts the 3-phase current to reposition the main stator magnetic flux vectors, always maintaining the 90 electrical degree torque angle from the rotor magnetic flux vectors. The rotating 3-phase current creates rotating stator magnetic flux vectors by varying the stator current level of each phase, so that the rotating stator magnetic flux vectors always lead the main rotor magnetic flux vectors by 90 electrical degrees and always pull the rotor toward them. The resolver continues to transmit the rotor position to the CMSC, allowing the main stator field currents to be properly adjusted to continue producing torque. Once the VFSG gets up to sufficient speed, 700 RPM, the CMSC will determine rotor position by using a sensorless algorithm to sense voltage. This allows full closed loop control and maximum torque. After the main engines start, the VFSGs change to generate mode, and the generator control unit, GCU, takes control of the VFSGs. In generate mode, the VFSGs supply power to one of the 235 volts AC buses. To generate power, 1. The permanent magnet generator supplies 3-phase AC power to the GCU. 2. The GCU supplies a DC pulse width modulated voltage to 2 input leads of the 3-wire, 3-phase exciter stator winding. 3. The pulse width modulated voltage to the exciter sets up a magnetic field in the exciter air gap that is stationary relative to the exciter rotor. 4. These actions cause 3-phase AC to flow in the exciter rotor. 5. The 3-phase full-wave rotating rectifier assembly on the exciter rotor converts the AC to DC. 6. The DC supplies the VFSG main rotor, causing a magnetic field in the rotor. 7. As this magnetic field rotates, it causes AC to flow in each of the main stator windings. 8. Current flow through the stator is supplied to the generator loads. The 3 main stator windings are connected to terminals T1, T2, and T3 on the terminal block. The feedback voltage signal from the point of regulation is monitored by the GCU, which then adjusts the excitation voltage to the exciter stator to keep the output voltage at 235 volts AC. Auxiliary contacts within the GCB provide feedback signal to the GCU for GCB position, open or closed. Generator CTs measure output current of the VFSGs and feed a proportional signal back to the GCU for current monitoring. The VFSGs have a disconnect feature to protect the main engine gearbox from damage. The main component involved in the VFSG disconnect is an input shaft that mechanically connects the VFSG to the main engine gearbox. The input shaft of the VFSG can be disconnected from the gearbox either thermally or electrically. Also involved in VFSG disconnect are the plunger and disconnect solenoid. To better understand the process for VFSG disconnect, let's take a look at a different view of the input shaft and zoom in to get a better view of the plunger and disconnect solenoid. The plunger contains an internal spring that exerts an upward force. The disconnect solenoid contains a push rod that fits inside a notch on the plunger to keep the spring from moving the plunger upward. The push rod sits on a solder pellet internal to the disconnect solenoid. During thermal disconnect, when the VFSG sump oil temperature exceeds 390 degrees Fahrenheit, 199 degrees Celsius, the solder pellet melts and allows the push rod to withdraw into the disconnect solenoid. The plunger is then free to move upward from the force of its internal spring. A manual disconnect occurs when the VFSG disconnect switch is engaged. A signal is sent to the disconnect solenoid, causing the push rod to be magnetically withdrawn into the disconnect solenoid. Going back to the original view, you will be able to see what happens after the push rod is withdrawn into the disconnect solenoid and the plunger moves upward. Zooming in on the plunger end of the input shaft shows that normally there is space between the plunger and the input shaft. When the push rod in the disconnect solenoid withdraws during a thermal or electrical disconnect, the plunger is allowed to move upward and make contact with the input shaft. As you can see in the close-up view, the input shaft has a threaded end where the plunger makes contact. This will cause the input shaft to unscrew itself as it rotates. Now, let's watch the disconnect process occur in slow motion. The plunger moves upward after the disconnect solenoid push rod is withdrawn. The rotating input shaft unscrews itself from the gearbox end of the input shaft. The end result is that the VFSG input shaft is no longer connected to the main engine gearbox. Click the forward arrow to learn more about thermal disconnect. Thermal disconnect offers protection for oil over temperature. The disconnect device thermally activates when the VFSG sump oil temperature exceeds 390 degrees Fahrenheit, 199 degrees Celsius. If there is a thermal disconnect, the disc lamp on the flight deck P5 overhead electrical panel illuminates, indicating a loss of the primary magnet generator. Click the forward arrow to learn more about electrical disconnect. Control and protection of the VFSG, including electrical disconnect, is provided by the Generator Control Unit, GCU, Bus Power Control Unit, BPCU, and Main Engine Data Concentrator, MEDC. On the P5 electrical panel in the flight deck, the VFSG generator drive lamp is illuminated when there is either a VFSG low oil pressure condition or a loss of the VFSG permanent magnet generator. Permanent magnet generator stator wires are used to sense a rotor bearing failure in the VFSG. In the event of a rotor bearing failure, The GCU sends a signal over TTPC to the BPCU. The BPCU uses the Common Data Network to signal the Common Computing Resource and then the Remote Data Concentrator. The Remote Data Concentrator uses the Controller Area Network bus channels A and B to communicate with the Cockpit Display Unit. The Cockpit Display Unit uses the captain's 28 volts DC instrumentation bus to illuminate the drive lamp for the affected VFSG. When the VFSG oil pressure is too low, the low oil pressure LOP switch will close. The low oil pressure signal is monitored by the MEDC. The MEDC uses the Controller Area Network bus to communicate with a Remote Data Concentrator. The Remote Data Concentrator communicates with the BPCU over the Common Data Network. The BPCU uses TTPC to communicate with the GCU. The GCU then sends a signal to illuminate the drive lamp. To electrically disconnect the VFSG drive, the flight crew pushes the drive switch. The generator drive disconnect switch provides a ground to the Cockpit Display Unit 28 volts DC. The Cockpit Display Unit then sends a data signal out to the Common Computing Resource. After sensing that the VFSG drive disconnect switch has been actuated, the Common Computing Resource supplies a 5-second pulse to the GCU through the BPCU. The 5-second pulse allows the BPCU and GCU to sense and respond to the switch actuation. The BPCU controls the command for the Remote Power Distribution Unit, RPDU, Solid State Power Controller 28 volts DC source. The RPDUs, RPDU22 for the left channel and RPDU21 for the right channel, supply 28 volts DC for the disconnect switch. The RPDU Solid State Power Controller provides a 5-second pulse to the high side of the disconnect solenoid. The BPCUs also send the command over TTPC to the GCU. The GCU trips the generator control breaker, then provides a 4-second ground path to the low side of the solenoid. The GCU controls the return of the disconnect solenoid through its own internal circuitry. A white bar is shown on the P5 panel when the drive has been disconnected. Note, the GCU inhibits the VFSG generator drive disconnect request when the related engine fuel cutoff switch is in cutoff. Click the logic button in the diagram to view more detail about the logic for VFSG oil monitoring and manual electrical disconnect.